Hello, folks, and thank you for attending this presentation of the work we did last year called Midas, where we systematically protect the Linux kernel against TOCTTOU vulnerabilities, which, as we just heard in the previous talk, is a possible attack for the Linux kernel. This work was done at EPFL at the Hexhive lab. So first, let's try to understand what a TOCTTOU bug is. TOCTTOU bugs are an example of a class of bugs known as double fetch bugs, where the kernel is reading from untrusted user space data, which is typically passed as arguments twice. So if you look at the right out there, we show a very common paradigm, which is the TOCTTOU bug, where the kernel first reads data in order to validate it and perform checks on it. And some at later point, if the checks succeed, it reads the data again in order to use it. The problem is that because the data is held in user space memory, it can be changed between these two times, thus leading to a possibility that the second read is going to return invalid data and there's going to be some sort of exploitable bug in the kernel. In fact, this sort of bug is not limited to the Linux kernel. These have been found in kernel modules and is inherent to the design of syscall wrappers such as seccomp. This sort of bug has also been found in hypervisors, including KVM, and in trusted execution environments such as TrustZone. In fact, for the Linux kernel, I list a couple of CVs out here which have led to complete compromise of the system or significant information disclosure. So TOCTTOU bugs exist across a bunch of security critical interfaces, and they are a problem. To make it even more difficult, TOCTTOU bugs are easy to exploit, and I'll tell you why. Well, first of all, you need an exploitable TOCTTOU bug within the kernel. You need a function such as sigaction, which takes a parameter where there is data stored in user space memory. In this case, the second argument. Let us take hypothetically that this argument points to a configuration struct within which there is a variable x. And you see there are two reads of this variable x. The first read is used for validating against, say, a length. If you read the value 0, all good, you're fine. However, before the second read, it is possible that the attacker in a second thread is able to modify this to an invalid value, which means that the access is going to be out of bounds, thus leading to arbitrary memory leakage. All that an attacker needs is just two user space threads, which is a very low capability. With two user space threads, the attacker can use one to call the syscall with valid parameters, and then use the second thread to modify these parameters between these two reads. So in fact, it's very easy to exploit this sort of bugs. So this is where Midas comes in. So instead of going throughout the kernel and fixing all of these bugs, we want to have a systematic way of fixing this. And we realized that the way to fix this is to honor the inherent assumption in the kernel's code. The kernel developer expected that these two reads are going to in fact read the same value. And our fix is to ensure that the system does in fact read the same value, 0 in both cases, by making it impossible for the attacker to visibly change the value in memory. For this, we have two insights. We use existing parts of the Linux kernel. We do not have to rewire the entire Linux kernel. First, the Linux kernel uses transfer functions to read from user space data because of protection known as supervisor memory access protection. Second, we leverage page tables, which allow us to temporarily protect pages as read-only. So Midas enforces a very strong invariant that throughout a syscall's lifetime, that is from the time a syscall starts until it ends, every read to one user space object will return the same value, thus honoring an inherent assumption. How does Midas do this? First, after the syscall starts, as soon as the syscall touches a user space data, just like Midas's golden touch, that page becomes protected. We call this a snapshot. This snapshot is used to provide the same value to the syscall on every subsequent read. Of course, when the attacker does try to modify it, this is legal, so we actually make a copy in user space. And this copy can be updated. And when the syscall finishes and it no longer requires a snapshot, we are able to discard it. In essence, Midas implements a multi-versioning system for user space pages. And for this, we use a state machine. Let me explain how the state machine works. In the beginning of time, every user space page is unprotected and unique when there are no syscalls using it. Now the syscall started, and on the first touch, like I already said, we need to create the golden copy, the snapshot. This is when the page becomes protected and unique. On the first touch, we make sure that the page is read-only, which means that no other concurrent thread, whether it's user space or kernel, can modify this without setting out a page fault. At this point, there is still a single copy in the system because that's all we need to protect this snapshot. If there is a concurrent write, that's only when we incur the extra cost of having to create copies in memory, and now we have 2 of them. In this particular case, the page is unprotected because the latest copy, the one holding 42, does not need to be protected and allows concurrent writes from user space and any other threads. However, there is multiple copies, so this is the third state. In the case there are multiple syscalls running at the same time touching the same data, it is also possible that the page is protected and copied. However, when the syscall ends, the snapshot is discarded and we go back to the initial stage where the page is unprotected and unique. So how does Midas manage to do all of this? Well, there are a few key events Midas needs to track. First, Midas needs to know when a syscall is reading from user space memory, because in the first case, we need to mark the page as golden, and later we need to read from that golden snapshot. The great news is we already have transfer functions such as copy from user. That's the Linux terminology. There is similar terminology for XNU or FreeBSD. And so the OS explicitly knows every user space read, and we instrument this function in order to implement this extra functionality. The other key event we need to track is when there is a concurrent write. So copy from user also protects the page, making it read-only. And we have page tables which are hardware managed access control, where we are able to set permissions so that any concurrent write which could modify this data now raises a page fault. By modifying the page fault handler, we can ensure that we do the correct duplication and mapping of pages so that the snapshot is protected and the latest copy, which is the new copy, is now mapped in user space pages and is available for use. So Midas is able to use existing OS and hardware features in order to protect snapshots. So instead of having to look through the millions of lines of code of Linux, we only had to look at 2 functions. We made an addition of around 1,000 lines of code, and we modified only 26. So in conclusion, Midas is able to systematically mitigate TOCTTOU bugs. We do this from concurrent writes in both user space and kernel, even though today I just talked about the attacker from user space. However, Midas also protects against confused deputy attacks, where the attack might actually be coming from a separate kernel thread. For this, we leverage the page tables in order to protect pages, and copy from user in order to create golden copies and duplicates as necessary. For this, we implement a per user space page state machine where every page can be protected or unprotected, copied or unique. And we do all of this while maintaining a low average overhead of only around 3.4%. We computed this on the NASA parallel benchmark and a Foranis test suite, as well as Apache Nginx. The artifact, we submitted this for evaluation, and we were able to get all three artifact evaluation badges. What that means is not only can you find the code for the Linux kernel at this address, you can also find a find a disk image which can run on virtual machines, and you can flash onto a real machine and run it yourself. So overall, this is why we believe that Midas is able to provide comprehensive double fetch protection at low overhead. Thank you for your time, and I would welcome questions.